Hi everyone, so this is going to be the next topic in our discussion where we're going to talk a little bit about ideal gases as well as the two main types of gases that we're going to be dealing with. Right before we start though, we'll do a very quick practice question. So pause video, work on yourself, and we'll go over it in a second. All right, so what we're going to do here is they tell us that they want us to show that the average energy per particle is going to be equal to 3 tau, sorry, if the energy is approximately equal to pc. So, and p being the momentum of the particle. So what we could do is we start off with this, and then we can take our equation for momentum. If you recall from before, or actually it says right here, this is something that we derived in, I believe, the previous lecture notes, that the de Broglie wavelength was equal to h over p. So we just do the same thing, except we're going to replace that h with h bar. Um, and we end up having this. Then we can also replace lambda with 2L over n, pretty much the equation for a standing wave wavelength. And we end up getting this equation right here. And then we're going to also, since we're talking about energies and stuff, and average energy usually means that we're going to have to take into account the partition function. Remember, the main thing that whenever we see that phrase like average of anything, usually we have to do that whole sum of the energy times the probability of it occurring. So here we're going to need the the partition function, that we're going to need to make sure that we substitute in this for our energy. So we do that and we get this equation. Of course, we want to do an x substitution again, like always, in order so that we can be able to derive this a lot easier, or integrate it a lot easier. When everything's all said and done, we end up getting our integration to boil down and simplify to this phrase. This is actually a known number. It's surprisingly just 2. And then what we end up getting is that the partition function's equal to this term, right? So then from here, the average energy. So if you remember one of the equations we had, when we took the average energy as being, a sum of blank times the probability, we actually found that one way of writing it was like this, so that we didn't have an infinite sum. So now that we have the partition function, we can very quickly take the ln of this and then take the partial derivative with respect to tau. What I like to do is I like to set, I think I've said this before, but I like to separate my functions as best I can, especially when we're dealing with an ln, so that you have one term that is all constants and one term that only has the variable. So right here, that's what we have. This is going to go to 0, and this just becomes 3 over tau. And then from here, you can already see that we end up getting the 3 tau function, as I said before. And that's pretty much it. So this is going to lead into something that we're going to call, what we're going to talk about is the Fermi-Dirac distribution function. So we've talked before about when the concentration is lower than the quantum concentration, then we consider these as being an ideal gas of non-interacting atoms, and that we can basically use a lot of the things like PV equals nRT, for example, when dealing with that. That we won't have to go into this discussion of quantum effects. That basically the gas is in what we would call the classical regime. Now, we are going to actually talk about some cases when that concentration does get a little bit closer to the quantum concentration and we're no longer in the classical regime. And that's going to require our discussion of the two different types of gases. Now, I'll explain what I mean by that in literally a second. But we're going to actually talk about what we call the average occupancy, or the number of particles that are occupying specific orbitals. And this average occupancy is what we're calling a distribution function. So the distribution function is going to be represented by this F term, and it's going to be based off of the orbital energies, what particles are in what energy orbital. And as you know, the orbital that we're talking about is referring to an energy state that's satisfying a Schrodinger equation. So, as you know, for gases, they are occupying certain energy orbitals. Um, so there are two types of gases, and this is what I was trying to mention before. There are fermions and bosons. So this distinction only matters when we start getting towards the quantum realm. So when we're in the classical regime, it doesn't matter whether a gas is made up of fermions or bosons, because uh, each particle has so much energy that they can be in whatever orbital they want, that we don't have to make a distinction about what type of particle it is. However, once we start getting into the quantum realm, where the amount of energy is actually being limited due to the low temperature, or the low, high concentration, then we do have to start making these distinctions between whether we're dealing with a fermion or a boson. So fermions are particles that have half integral integer spins, and bosons have zero or integer spins. Now, what this means is that there are a few occupancy rules that are going to come from this. So, for example, one rule that we end up getting is that an orbital can only be occupied by an integer number of bosons of the same species. Uh, by any integer number of bosons. So when we have a gas made of boson particles, then any of the orbital can be occupied with however many particles we want. So, you know, we could have all the particles at the ground level. We could have all the particles in the first level. We could have it split half and half. Doesn't matter. We're not being limited when we're talking about bosons. However, because of the spin nature of the fermions, it turns out that an orbital can only be occupied by either zero or one fermion of the same species. And this is what we call the Pauli exclusion principle. Now, I wanted to clarify this a little bit more, that when we say of the same species, we specifically mean spin up or spin down. So, what that means is a particle that's a fermion can be either half spin up or half spin down. Um, and when we are talking about the orbitals, then we can only have one fermion that's spinning up and one fermion spinning down, and that's it. Um, or I should say that's the most that we could have. Because as they say, we could also have just none of them. We could have only one going up or only one going down, or none at all. But for the most part, the idea is that when we're talking about fermions, we are limited to the occupancy of the particles. And like I said, this becomes a much bigger distinction as we talk about the quantum effects, where we're talking about low energy states. Okay, so what we're gonna first talk about is we're gonna consider a case, because we're gonna actually start off talking about the fermions first. So we're gonna talk about a case where you have a single orbital occupied by a single fermion. So the orbital can only be 0 or 1. Um, so that means that the energy could either be 0 or epsilon, because if it's not occupied, there's no energy. If it's occupied by one, then it's got whatever the base energy is for that orbital. So that means our Gibbs sum that we have, the grand partition function, when we write that out, will look something like this. Uh, this term representing no fermion, and this term representing one fermion. Then from here, we can find what the average number of particles is by just taking the fact that we can have one particle and dividing it by the Gibbs sum. And we end up getting this equation for the average occupancy. So our equation will end up looking like this. And this is what we call the Fermi-Dirac distribution function. This is going to give us the average number of fermions in a single orbital that has an energy of E. Now, one important note is that because of the fact that we can only have 0 or 1, uh, that means that the value of f is always going to lie somewhere in between those two numbers. Because if we take an average of all the orbitals, for the most part, there will be maybe some orbitals that only have one particle, some that are filled that have none of those species, and in total, it'll always end up being an average less than 1. So somewhere between 0 and 1. All right, so we'll do a quick practice with this. So pause the video, work on the cell phone, we'll go over in a second. All right, so what we're going to do here is use our Fermi-Dirac equation. So they tell us that we're going to plug in basically mu plus delta in for the energy states. So we can take the Fermi-Dirac equation first using this mu plus delta part, and it simplifies to this term. Mu minus delta, when we plug that in for the energy, it will actually simplify to look like this. But since we're going to end up having to relate this term to this term, what we're going to want is to make sure that this denominator looks like this denominator. So what we can do is actually just multiply the numerator and denominator by e to the delta over tau, and we end up getting this. So now these two terms are going to have the same denominator, making it very easy for us to relate them to each other. So they want us to show that this equation is true. So we'll just plug in what this is in for the mu plus delta and this in for mu minus delta to get this equation. So since actually we don't plug anything in for here, but when we do plug in this term in for this second part, we end up getting 1 over e to delta over tau plus 1, which is exactly what we got up here. So that means this equation is in fact true. All right, here's the next question. Pause the video, work on the cell phone, we'll go over in a second. All right, so here we're imagining a new case where now the occupancies could either be 0, 1, or 2, and the energies are going to be 0, epsilon, and 2 epsilon. And they want us to basically come up with a new average occupancy number. All right, so our grand sum partition function is going to look something like this. So no occupation, one particle, two particles. Easy peasy. So there's our grand sum equation. We can use a slightly altered equation for the number of particles. This time, since we're leaving our equations in terms of these lambdas, we can actually just keep that in there. So take the derivative of this with respect to lambda. Ends up being extremely easy. This drops out, this lambda drops out, and this just becomes 2 lambda. So we end up getting this. And then carry the lambda over zeta through, and we get this. So this is our equation for the average occupancy. All right, here's the next term. Next part. Pause the video, work on the stuff, and we'll go over in a second. All right. So now they want us to um, basically derive that equation again, but this time we're changing something. So it says this term doubly degenerate. And it actually says here that there are two orbitals that have identical energies. So what that's trying to say is that we can have a case where there are two particles, but they're in two different orbitals. So that's what's going on here. That basically we have two different cases where there's one particle to an orbital with an energy of E. So it doesn't really change much except for this 2 coefficient. Um, so we can actually rewrite this to look more like this. But once again, we pretty much do the same thing. We take the partial derivative. Um, Nothing really changes. We could actually pull a 2 lambda or 2e to the negative epsilon over tau out from each of these two terms to get this. And we can see here, which is one of the reasons why we rewrote this to look like a polynomial expansion or compression, I guess, is so that we can actually drop out, cross this out with one of these terms. And then it ends up looking something like this. All right. All right. So here, um, coming up with the equation for the chemical potential. So they say here that chemical potential is commonly referred to as what they call the Fermi level, and the value of the potential energy when the temperature is zero is represented by epsilon f, or the Fermi energy. So what this is referring to is pretty much the highest level that's achieved when each particle is given their lowest possible energy amounts. So, as we said before, um, when we're talking about low energy systems, fermions are only allowed to have 0 or 1 particles of the same species within a level. So the idea here is that if we have every level occupied to their maximum amount, um, EF is this Fermi energy is going to represent the highest energy value that's occupied. So here, they say that all orbitals of energy below this are occupied by 1 fermion. All the orbitals above are unoccupied, and all the orbitals that are equal to the Fermi energy are half filled. So yeah, that's pretty much the whole idea, that this is the highest level that can be organized when we're at the lowest possible temperature value. And this ends up giving us essentially that we could see that here, that the Fermi-Dirac distribution equation will end up getting this 1/2 value due to the fact that when we plug in E being equal to mu, then it just becomes 1/2. All right. Taking a step from there, we're going to talk about what they call the Bose-Einstein distribution function. This is going to be talking about bosons. So we're switching our discussion to bosons instead. So here, we're using kind of the same idea that E is going to represent the energy occupied by a single particle. And then if we end up having n particles of bosons, then and all of them are in that orbital, that means that the energy is going to be n epsilon. Now, if we do the Gibbs sum for here, it looks a little different than what we had for the Fermi equation, because now each one can have this energy. So our Fermi-Dirac equation will look something like this. We could just have this for each n term, so we could just write this as this term raised to the n power. So to make life easy, we could just replace this with x. The summation is going to look something like this, and it will end up simplifying to this term. And once again, finding the average occupancy, we do the exact same thing. Take the partial derivative, follow through. We end up getting x over 1 minus x. Substituting what we had for x in back into this equation, and we end up getting this. Now, it actually looks almost identical to the Fermi-Dirac equation. This is the Bose-Einstein distribution function. The only difference, though, is that instead of a plus 1 here, it is now a minus 1. Now, it doesn't seem like it would make a difference, but it actually does make a difference here. All right. So going back to the idea of classical regime and quantum regime, here what we can say is based off of that our equations for the occupancy equation, so the distribution functions, the gas is considered classical when this value, this average occupancy, is much less than 1. Now the reason for that is the idea that there are more available energy levels than there are particles. So we don't have to worry about issues of, oh, are we going to be really close with having a lot of particles in one spot or whatnot. So you can have a situation where there's essentially one particle and then there's a few orbitals that are completely empty and then another particle somewhere else. So we end up having a situation where it's in the classical when it's much less than 1. Here we go. So this is what I actually was hoping to see at some point, was this graph, because this really shows the difference. So here is the occupancy equation for the Bose-Einstein equation, and this is for the Fermi-Dirac equation. And as you can see, they end up merging together at some point when E minus mu is essentially 2, or 2 tau. This is what we call the classical regime. There's no difference between bosons and fermions. But as we go down here in the low energy ranges, we end up finding that there ends up being a drastic difference between the bosons and the fermions. Again, the fermions can only be between 0 and 1, because at the very lowest state, we can have at most one particle in the lowest possible and every low possible energy level. With the bosons, though, well, technically there is a case where we can have all the particles in one single orbital. So at the lowest possible energy level, we can technically have thousands and millions of particles all at the ground level. So that's why the Bose equation kind of shoots up like this, because we can have more and more particles going into the same level. While the fermions end up reaching this plateau. So here's a quick little recap of the important things. So in the classical regime, fermions and bosons are both the same. The occupancy is going to be much less than 1. But when we start to get towards that that quantum regime, low temperature range, then the fermion ends up still being less than 1, but at least closer to it, while the bosons will end up being drastically higher than 1. All right, so here, because of the fact that we can say, oh, the classical limit is when that occupancy is much less than 1, and that's true for either distribution, we can actually combine them together in order to kind of come up with a new statement. So what we say is, oh, in the classical regime, this term is much less than one. So if we just move this over and get rid of the ones, because it honestly doesn't really matter, we end up finding that this term would have to be much greater than one. Because if we tried to solve this, if this was plus one, then that means that this would be much greater than zero. And if this is minus one, it'd be much greater than two. So same thing. Basically, this is an extremely large number. If that's true, then that tells me that or tells us that the occupancy equation can actually just be simplified to look like this or approximated to this. This plus or minus one doesn't really matter if this E term is extremely large. So this ends up actually just equaling E to the mu minus epsilon divided by tau. So this is what we would call the another definition for the classical limit. That in the classical limit, we end up getting this relationship that essentially lambda is that the average occupancy is going to be equal to lambda times e to the negative epsilon over tau. So this is what they sometimes call the classical distribution function. So now we have three different distribution functions depending on whether we're in the quantum realm or the classical realm, whether we're talking about ideal gases or if we're specifying bosons and fermions. All right, we'll keep going for a little bit. So the next thing is a little bit more about chemical potential. So here, we can go back and talk about the whole average number of particles. Um, so if we basically just sum up, so with the chemical potential, it basically says that the total number of particles is going to be equal to our average number of particles. Now we know that the total number is just going to be the sum of this occupancy number. That makes sense. The occupancy number for every energy state is just the number of particles in each energy state. And the total number should just be the sum of all those values. So if we use our definition for the classical distribution, our equation ends up looking something like this. From here, then we can replace this with the partition function, which ends up turning into this. We can actually rewrite the lambda term, so it looks like this. And we pretty much come back full circle to that term that we had before. So again, this is just saying that we can find the chemical potential by doing this method. And this is exactly what we got in the previous classes. Now the reason why this is important is mainly because we can technically do the same thing, or what this means is we can do the same thing for the boson and fermion values. When we have, instead of using the distribution function for the classical realm, we could do the distribution function for the Fermi-Dirac equation or the Bose-Einstein equation, and we would end up getting a different function for that. So, but again, it's also just trying to lay down this concept that this is what we're defining as the chemical potential, and that by making this distinction, we end up getting these same equations. Once again, we can kind of use this towards the idea relating this with free energy. Again, we're just kind of rehashing a lot of similar things. So if you remember, the chemical potential and the free energy have this relationship. So when we plug in this, this expands to look like this. So taking the integral of this with respect to the dn, it will end up looking like this. So this will end up being the free energy that we get by basically using this mu term, this chemical potential equation. We also, since we now have the free energy, we can now find the pressure by taking the partial with respect to volume. That's pretty easy. The only term that has volume here is right in this concentration. So the taking the derivative will actually just make it 1 over negative 1 over v. And we end up getting our ideal gas law. And then since we know that the free energy is equal to this, we can actually look at the internal energy equation, plug in what our equation for the free energy, as well as our equation for sigma for the entropy, which is also actually dependent on the free energy, to get this equation. And as I said, just rehashing a lot of these same equations. Now, one thing that I want to note really quick, because I think we're going to be talking about it in a bit, is to remember that this coefficient, this 3 halves, is coming from the fact that we're talking about monatomic gases that are only allowed translational kinetic energy. And in those cases, there's only 3 degrees of freedom available, translating in the x direction, in the y direction, and in the z direction. Later on, we're going to find that there are other degrees of freedom that could be available. There will be things like vibrational and rotational, which will bring those degrees of freedom to 5 and 7 respectively. The free energy, which is weird that I didn't do that one first, but the entropy can be rewritten like this. This was the that equation that we had before. And then I'll end it with just this quick discussion of the heat capacity. That now that we have an equation for the entropy, we could just work it through and get an equation for the specific heat. So same old things that we've done before. All right, so we're gonna end the video there, and we'll do a few more practice questions, but we will be doing more questions with the Fermi-Dirac equations and the Bose-Einstein equation. So if you have any questions, please let me know. Otherwise, I'll see you later. Bye.